Hello, welcome to this video. In this video, we will start working on reversed Carnot cycle. Now, we are familiar with Carnot cycle in a power producing like steam power plant, right? A Carnot cycle is the one which gives you highest efficiency because it involves all the processes in the cycle which are reversible, that also internally reversible. So, a typical Carnot cycle in a PV diagram looks like this. So, it has got two adiabatics and two isothermals. So, heat should be added in isotherms, so at constant temperature, and expansion in a turbine is expected to be in a adiabatic process. So, heat was supposed to be added in constant temperature and the work was supposed to be done with PV power gamma is equal to constant, that is reversible adiabatic. So, essentially you will have two isotherms and two adiabatics. So, this is what is Carnot cycle. So, if you talk about Carnot cycle, it will be in the direction of this, that is heat is added here and heat is rejected in condenser here. The top portion is like boiler and the bottom portion is like condenser where heat is rejected, alright. But we are talking about reversed Carnot cycle. So, we are going to reverse the direction. So, that means it take the heat from this lower temperature reservoir, that is, let us call it as QL, whereas heat is rejected to the atmosphere, that is at higher temperature, let us call it as QH. So, heat transfer with respect to higher temperature reservoir, let us call it as QH. Now, let us reverse the direction of heat transfer. I mean to say, in a proper Carnot cycle, the direction of process will be towards right. So, we will have to reverse it. So, let me highlight that. So, it will be in this direction. Okay, it will be in this direction. Now, we can start giving the numbers. So, if this is the evaporator, you can call it as heat is removed from here 1 to 2. Yeah, this number can vary little later. Do not worry about the numbering right now, because okay, let me quote otherwise. I'll start 1 from here, because that is what we do in vapor compression refrigeration as well. So, 2, 3, 4. So, 1 to 2 is compression, then 2 to 3 is heat removed from the refrigerant or heat added to the higher temperature reservoir. 3 to 4 is expansion, then 4 to 1 is the process where heat is removed. So, again these two are again reversible adiabatic process and this is again temperature constant process. Now, how does it look like in a TS diagram? It is quite easy in TS diagram. So, 1 to 2 is, so as we said, this temperature versus entropy diagram. So, you have 1 to 2 which is reversible adiabatic or isentropic. So, isentropic process looks like this PV power gamma, or if it is reversible adiabatic, entropy is also constant. So, it looks like this. Then constant temperature in a TS plot would look like this, alright. So, there is constant temperature, as usual heat is taken out from the refrigerant. So, this QH again, then 3 to 4 is expansion, that is with reversible adiabatic expansion. So, this is entropy constant or PV power gamma is equal to constant or entropy is equal to constant. Then again you have this process where you are calling this as constant temperature, heat removal from the space or heat addition to the refrigerant. So, you can always look from perspective of refrigerator or refrigerant, but whenever we write the cycle, we are much worried about the refrigerant. So, for refrigerant it is the heat addition, but From the space, confined space, you are removing the heat, you call it as QL. Now, this is what a simple reversed Carnot cycle would look like. So, we have started the compression as 1 to 2, heat rejection as 2 to 3, then expansion as 3 to 4 and 4 to 1 is heat addition to the refrigerant. Now, we talk about coefficient of performance in refrigerator, coefficient of performance. Now, how do you define coefficient of performance? It is desired output by input. Now, very important, we are not just saying output, we are saying desired output. Now, what is desired in a refrigerator? In a refrigerator, heat removal is what is desired. Now, heat removal is what is desired, that is 4 to 1, all right. So, desired output is 4 to 1. So, how do you write? That is heat removed, that is QL. Heat removed divided by the input is the work which we are giving. The work which we are giving is here in between 1 to 2, that is you are giving compressor work, that is electricity to the compressor. So, work you are giving. Okay. Now, this can be further simplified like from first law of thermodynamics. You know that work can be rewritten as heat supplied minus heat rejected. So, this can be rewritten QH minus QL by QH minus QL. Now, very important, whenever we talk about QL, so already QL is here, all right, 4 to 1. Now, QL can be further simplified like from the concept of entropy, we know that Q is given by temperature multiplied by change in entropy. Now, from there I am drawing this equation. Now, QL can be lower temperature. Remember, we are operating between only two temperatures. Now, this is a constant temperature, this is a constant temperature, all right. So, I will call this as TL is equal to T1 is equal to T4. Similarly, here T higher temperature is equal to T2 is equal to T3. So, we are operating between TL and TH, that is it. So, whenever we talk about the process 1 to 4, TL and entropy change, I can write it like S1 minus S4. Okay. Similarly, I can simplify for QH. Now, QH is equal to TH S2 minus S3. Now, I will come back to this equation. Now, I have QL and QH and QL and QH. So, TL into S1 minus S4 divided by QH is TH S2 minus S3 minus again QL is TL into S1 minus S4. Now, if you look at this diagram, you know that S1 is equal to S2 and S3 is equal to S4. So, that means S2 minus S3 and S1 minus S4. So, this cancels out. You will remain with COP is equal to TL divided by TH minus TL. So, this is the equation of reversed Carnot cycle for COP. We will see in the next class. Thank you.